Most of us learn that the human brain is able to adapt to change pretty quickly. And that is a good thing. It's called neuroplasticity. You may have heard that term. This study really challenges the core classic narrative and shows that the brain activity can stay relatively stable even after an amputation. That doesn't necessarily mean that plasticity is wrong. It just means that stability and change can coexist. Neuroplasticity. The term gets tossed around so often that it seems like it can mean pretty much anything you want it to. Some neuroscientists really hate the terminology because it is so general, so unspecific, and it's kind of a loaded term. Let's talk about why. There are broadly 4 different layers to this subject. We've got synaptic plasticity, which is happening at the synapses, and this is about connections that can get stronger or weaker with use or experience. Sometimes people mean to talk about new synapses forming based on experience, like learning to play new guitar or learning to play the piano. These activities can actually help you generate new synapses. We've also got neuronal plasticity, and this is happening at the level of neurons, which is about new neurons being developed. Contrary to popular beliefs, we're not born with a fixed number of neurons because studies have shown that people can generate new neurons well into our adulthood, well into our 80s. So keep studying because we will need to use it for the rest of our lives. We also have network level plasticity, and this is about brain areas that can actually interact with each other. And depending on different changes in the environment or stimuli, we can actually change the way we talk to different brain regions within the network and see how efficiently or less efficiently they can communicate. That happens. Finally, we have functional remapping, also called reorganization. And this is the big one for today's video. After losing a body part, the brain supposedly take over kind of a real estate for another body part. It's like the brain regions responsible for those lost limbs, now that they're no longer needed, they kind of take over a new function for a body part that still exists. Think of it like kind of a city that has a bunch of train stations. We've got subway station that may be used in a high traffic area, and sometimes it may not be used at all in a more rural area. Well, if you're trying to be more efficient with your economies of scale, then you may want to reroute trains so that you can meet the demands of high traffic areas, right? If no one ever uses a part of the town, then maybe you should not have train stations. And this is kind of how the functional remapping happens. Depending on the needs of the brain function, we can actually reorganize how information travels from the body to the brain. This type of plasticity matters a lot to people who use prosthetics and for people who are studying brain-computer interface applications. For years, we've believed to think that injury or amputation can trigger a huge amount of change in the body map. This is talked about a lot in the context of stroke rehab and phantom limb pain, which is the topic of today's video. If a brain region moved on from representing a lost limb after an amputation, then you would think that there should be no sensation. But people with amputations actually talked about feeling weird sensation and pain in their lost limb. Itching, burning, or otherwise just weird sensations in an arm or leg that doesn't exist. Phantom limb vibrations, kind of like ghost notifications.
Am I hallucinating these notifications?
The new study seems to think that this is more to do with the physical thing about the way brain organizes the body versus just psychological. The somatosensory cortex is one of the brain regions that help you feel things, including pain. Although we don't want to feel pain, but we do want to feel pain because otherwise we'll never know when we need help. The body's SOS signal needs to be taken
seriously so that we can go to the hospital and be able to take care of ourselves.
Scientists have studied how movements in different body parts are being picked up by this region. And they've actually created a whole map show the different body parts corresponding to different brain regions. You may have seen this bizarre looking illustration. It's called the Homunculus. This map shows how different body parts are related to different regions in the brain. So each cortical area representing different body part. A classic idea is that if you lose a hand, so-called hand zone gets replaced and kind of taken over by something nearby. Let's say, like the face. The original drawing is from the 1930s, but today we've got precision fMRI, so we can actually detect the map of individual fingers and lips much more closely and precisely. So this new study scanned people before and after their amputation surgery, and they tracked these people and their brain activities after a year and even 5 years later. Kudos to people that are actually able to participate in this study and willing to participate over what could be the most traumatic experience in their life. So the study was actually done over a 7-year period. That's a long time for people to participate in over coronavirus and all that. Losing an arm, that's a significant experience. Same people, multiple time points, longitudinal study. They've also looked at chronic amputees as well as controls. What's surprising is that the body map didn't actually change after a year, even after 5 years out. So people could still move their intact fingers just fine. And even when they just merely imagine moving individual fingers on the missing hand, they were able to light up the exact same brain spots. And this happened across time and across different participants. So pretty remarkable here. And even for individual fingers, look at how similar these activity patterns look before and after an amputation. If you look at the color-coded finger maps, that's even clearer. When they try to decode which finger corresponds to which brain activity, they're pretty accurately able to classify that as well. It was well above chance level performance, and it stayed that way for pre and post-op. So this really pushes back on the idea about the brain and how the plasticity works. The brain doesn't just rewire the entire map of our body after surgery, and something as traumatic as losing a body limb. The scientists also check the flip side. If a hand area isn't getting taken over, then the rest of the body map shouldn't take the extra real estate as well, right? And that's exactly what they see. The lip patterns stayed pretty stable. So you may be wondering, what if the body map actually shifted or expanded or shrank? This is a valid question. So they looked at the boundaries of this body map. And what they found is that the lip map boundaries, you can see how consistent they are across time. So in summary, both hand and lip body maps look stable. And because merely imagining finger movements can still reactivate those brain regions, the same spots. The study suggested that the somatosensory cortex maybe isn't just passively relaying information about the environment, maybe they're actually taking up more of a boss role that supports resilience of the body map that we have. If remapping isn't the driver here, we may need to consider other contributing factors like weird signaling from the peripheral nerves, changes in the spinal cord or thalamus, expectation, attention systems, maybe even other network level mechanisms. But the point is, we don't need to solely focus on this face invades hand kind of a story of remapping or reorganization to explain the phantom limb experiences. On the other hand, this study brings up a lot of hope and promises for people who use prosthetics and the future brain-computer interface applications. If the cortical brain map doesn't change, then we can use the precise map of different parts of the body, like the individual fingers, to help patients use their prosthetics more like their own body parts. Basically plugging into what's already there instead of creating a whole new thing, which could help make the training more efficient, decoding better, and make the movement control itself more natural. We may also want to change the way we strategize drug development or rehabilitation for stroke patients. We don't need to focus solely on reversing the map that we have of the body for treating phantom limb pain, because stable representations exist and it seems to generalize to other human subjects. So what we should do rather is we should leverage the anatomy that's already there. A great example of this is seen in people with spinal cord injury. People actually received epidural stimulation and walking training were able to walk. Basically, use what's already there and amplify to our advantage. Another, a bit nerdier angle that this paper points to is potential improvements in the way we do research. Some older studies for imaging analysis have focused on winner-takes-all kind of a strategy when it comes to phantom limb representations. But ignoring the stable cortical patterns can really lead to biased conclusions. This is kind of like the challenge that we have with the electoral college in the US election. When the winner takes all of the votes for each state, then we're actually removing all the potentially useful information about the spread of the votes, right? That don't particularly win. With brain maps, stable patterns matter. And this study uses pattern level evidence and leans on it. So where do we go from here? For drugs and rehab, don't obsess over reversing the cortical representation that seems pretty stable. Rather, let's use what's already there and build from there. This study really challenges a core classic narrative and shows that the brain activity and their widespread body map can stay relatively stable even after an amputation. That doesn't necessarily mean that plasticity is wrong. It just means that stability and change can coexist. And I think the society, science, and industry can plan for both stability and change. If this was helpful and you want more content on surprising neuroscience facts and the latest news in neuroscience that matters for your day-to-day life, like, subscribe, and share with a friend that might also enjoy the topic. See you next time.